recapping the process for the integral method, what you want to do is first you assume a functional form for u. That is, we say I've got some polynomial or some equation that tells me generally how the boundary layer velocity depends on position y, and then you normalize that by the length. So it would be u y as a function of coordinate y between 0 and delta m. And then as delta m changes, you can then solve for the things that you care about, like shear stress or the energy part of it, delta t. You'll be able to solve for the convexity coefficient. Okay, so you have that functional form of u. You substitute that into the integral forms of the boundary layer. It should lead to an ODE. That ODE is going to be in terms of the delta that you are trying to solve for, delta m or delta t. So you have an ODE in that delta variable. You solve that ODE, and then the boundary layer thickness, delta mx, allows for estimation of the shear stress and friction coefficient. I guess the part that's not explicitly stated here is that when you assume a functional form of u, you have to do something to get that form to match your problem. So you start by assuming a general form, say a polynomial with unknown coefficients. You have to solve for those coefficients by enforcing things about your problem. So yeah.
So, sorry, what you were saying, I forgot.
Okay, yeah, no problem. So what we're going to do is we're going to go through assume a form of u, and then get to actually see how this executes out. So here's the integral form again. Sorry, it's very small, hard to see, but that's the integral form. And we're going to start by assuming a functional form. But before we do that, let's actually figure out which of these terms we're going to throw out for our example. So the example we're going to start with is just a simple boundary layer condition where there's nothing, there's no velocity injection. The pressure gradients are small in the x direction. And then it's not a shear-driven flow. So let me just zoom in a little bit, and we can kind of pick on this equation a little. So let's figure out from this which of the things in this equation for a normal, let's say a typical boundary layer, would go away. So going through this, let's see, we would start with looking at, I said there's not any significant pressure gradient in the x direction. So if we know that there's not a significant pressure gradient, we know that du infinity dx is 0, essentially. So if this is 0, then this whole term goes away. We are saying that there's no injected momentum there's no injected velocity at y equals 0. So that v y equals 0 would be 0. So this would be go away. So that makes this whole term go away. And then for a non-shear driven flow, or just a conventional flow where u infinity is at a constant velocity profile, there's not any shear stress tau y at delta m. But there is still shear stress at the surface, right, tau s. So this term here, or that part of it, goes away. We do still have momentum change as a function of x position. And then also you're integrating that over the y profile, so that first term sticks around, and then the tau s in the last part of it sticks around. So with that, I guess we would end up writing our simplified equation. Let me just zoom back out here. So our simplified equation is just going to be d dx of the integral from y equals 0 to delta m u squared minus u infinity times dy. And that's equal to then just minus tau s over rho. Tau s over rho. That's just a simplified form. So this is now the integral form that we're going to actually solve in our example. Giannis.
So what, just so I understand a little more about why we can neglect the injected momentum, what kind of flow would that actually be important in?
So that would be important in a case where, actually I think the homework problem is going to potentially address this, but it is a situation where, let's say you have like a pipe, right? And that pipe has little perforations in it. And you're using that to, let's say, like pasteurize milk or something. And you have steam that's being injected into some other liquid. So you have flow going on the outside of the tube in one direction, and then you have steam perforating through and it's like injected into the X direction flow. So that would be an example. I think I gave the example of a membrane where you have kind of a similar situation. But that type of thing is where that would show up. And then I guess what's important about that is that contribution in the y direction to the momentum is small, I guess, compared to the overall x momentum. So you can still neglect, say, the overall y momentum equation, but the contribution to the x momentum is not trivial. So think about that. Like you're putting y velocity in. It is changing the x momentum because it's got to be conserved here. So you're really looking at the change in x momentum as the important thing through a contribution in y. Okay, so that answers your question. Okay. Okay, so this is the example we're going to go through. So we're going to assume a velocity profile that is again a function of y. So it'd be u over u infinity is some function of y over delta m. And let's, I guess, choose a function that lets us do things that we want to do in this problem. So what we would assume, let's say, is actually, before we assume a velocity profile, let me tell you what the conditions are that we might want to enforce, and then we can decide which of those are important. Okay, so let's see. First thing we might want to do, let's see, conditions to enforce. First thing we might want to do is enforce no slip at, so u at y equals 0 would be 0, right? That's no slip at the surface. That would be a good thing to enforce usually. Second thing we might want to do would be make sure the free stream velocity is what we call recovered. So that's just saying u at y equals delta m is equal to u infinity. So that's saying my u profile, u of y profile at delta m, this is a subscript here, so u y at delta m would be equal to u infinity. We're just enforcing that condition, just like we are at the y equals 0 condition. Another condition to enforce might be the shear stress at the boundary layer edge is recovered. So that would be saying, mu times partial u with respect to y at y equals delta m is equal to 0. So these are like, we're taking these physical concepts and then just coming up with like mathematical expressions for that we would then enforce. The last thing, not really the last thing, but an additional thing would be saying that the differential x momentum is conserved or is satisfied at some position. So that might be saying, you take the full momentum equation, we just write it out, it would be rho u partial u with respect to x plus v partial u with respect to y is equal to minus dp dx p infinity plus mu times second derivative of u with respect to y. And then all of that would be evaluated at some position. So we could say, all right, let's evaluate that at y equals 0, for example. But you could do that anywhere. You could do it multiple times anywhere, right? So the conditions that you might want to enforce would be something like this. So with this stuff in mind, I guess now would be a good time for the top hat questions. Let's put that up. All right, so this question says, when choosing the number of terms and correspondingly the number of unknown coefficients to include in an assumed velocity profile, which of the following statements are true with an E, hopefully? So pick all of them that apply, right? So there's 5 of them. Okay, so we have a few things. Let me look at the correct answers. So a lot of you said too many terms, it may be impossible to find enough boundary conditions or enough conditions to impose. That one is not true. That is not an answer. And the reason is I could say that momentum one, that conservation of momentum. I can do that at any point multiple times. So that one in particular, you could have an infinitely many conditions to impose, or you're just making sure it matches everywhere. So the one you're really sure on, that was the wrong one. So the other ones, let's look at the answers here. Linear models always naturally enforce. Most of you got that correct. Linear models don't necessarily enforce the no-slip condition. Okay, so the correct answers are A, B, and E. More terms, you're going to have greater flexibility in matching the real velocity profile, usually. So that is generally true. More terms allows more conditions to be imposed. That is true. And more terms in the profile makes the math more difficult. That's really what we care about, right? Making it easy. So that one's true. Okay, any questions on that? If you have enough data, let's say if you're going to develop a curve fit, right? You have enough data. As long as you have more data points than you have coefficients in your terms or coefficients in your fit equation, you can always fit that additional term. So what is like this is being a continuous equation, you can always choose additional points to enforce a condition. Right. So you at some point there's diminishing returns. Like you're not getting better by adding extra coefficients, but you can always add more.